All right, so today we're going to look at one other kind of data modeling. We've already kind of looked at it before, but it was more or less in passing. Let me see if I can find enough colorful chalk. Well, that's just great. There, now I got enough colorful chalk. Okay, so we've already looked at several different kinds, and that's typical. So in the data science engineering, blah, 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 it depends on what you're trying to accomplish. So we had one case, I'll use X and Y to represent the horizontal and vertical component of the drawing. We had one case where we were confident that the data points themselves were accurate. Perhaps they were the result of lab measurements, and we were interested in what happens between data points. Do you remember what fancy word we used to call that? It's like an old Helen Reddy song. It was anticipation, but it was a different word. Rhymes with it. That's way before your times. That was when your parents were in high school, just like me. We had interpolation was a tool, and the key thing about interpolation is the data model that we build by design goes through the X and Y points. It's supposed to. The error at an X, Y point for which we actually have a value is 0. And I actually drew this slightly incorrectly because with interpolation, we are limited to where? We're limited to whatever the range of observations is. If we're interested in something out here, our interpolating polynomial will give us a number. I mean, you can put an X in and it will produce a number. But we have no idea what's going on, all based on whatever the polynomial is, and it does the same at this end. And some of you experienced it on the second exam when you chose to use the Lagrange polynomial, but you had funny business up at the right-hand end. It had this little nick in it, and that's actually a consequence of the data itself, integer versus float. So it does funny business when we get outside the interpolation range. The next type of data model that we looked at we had our X, Y, we had some observations, and what color did I use? Green. Let me use my reduced size green. And we postulated some functional form that ran through these. So this is some function y equals f of x. And we adjusted that function, adjusted the parameters by
reducing the residuals.
That was how we measured how good that function fit. But the first way we did it.
By changing the betas, beta 1, beta 2.
Yeah, and how did you pick values of beta 1, beta 2? You pulled them out of your data. Okay, so try them there. Or guess and check, or whatever you were taught back in whenever you were taught that. That's not a very systematic way. It's very unlikely that you, Matteo, and Rory, and Elizabeth, and Michael, and Kylie, and Catherine, yeah, got them all, would get the exact same curve. You could, but it's pretty unlikely. Well, actually, you probably would, because one of you would get it first and you'd share it with everybody else. But if that was not the case, it's pretty unlikely you get that. It's not particularly systematic. Now, there is a way to extend this into a systematic approximation, which we'll look at unintentionally today. We can put this function into an optimization program and instruct that program, minimize the error between the observations and my function by changing the function values. But it's not the same as regression. It's a different way to do. End goal is kind of the same thing. The advantage of the optimization method is that it doesn't care particularly that the green curve, whether or not it's linear in functions of x to predict y. It doesn't matter. As long as the curve can be defined and it's continuous on that range, and the optimizer doesn't end up attempting to divide by 0, which happens quite a bit, it will attempt to produce a result. You, the analyst or engineer, have a very important step to do when you use an optimization technique, which is to plot stuff one more time to be sure that the computed curve plausibly passes somewhere near the data points. If you fail to do that, you do stuff like you get hypersonic weapons that take off in Beijing and land in the middle of the Pacific Ocean and make a big splash. For instance. The next data model approach we looked at that's good enough, was similar to this one in a sense, except that the green line now was stipulated to be a linear combination of functions of x. So one of the functions of x that we commonly use is x, and then an intercept. Another one we could use is x squared in x, x cubed in x, log of x in 3. And that was called
Linear regression.
Yeah, we'll just use the generic term regression. And we saw methods to do that. We could do it all by ourselves in primitive Python, which I would advocate is, other than knowing what's going on under the hood, that's not particularly useful outside this class. But we saw some other tools. Anyone remember what they were called? No, but I can go on the website and look it up from prior. Yeah, okay, good now. Sky, SK, Skippy, and I think I actually have to go look it up to see. I don't remember. So all these 3 pictures have something somewhat in common. Is that the x and y relationship is an attempt at a cause-effect. But there's one other type of data model we can consider, and that's what we're going to discuss today, which is a probability estimation model. And then next time, our next class meeting, we're going to discuss classification. And it's just a brief introduction into it because it turns out on the 18th, there's this stupid exam number 3. And then after exam 3, it'll be a miracle if even all 5 of you show up. Because anyone with half a brain will be able to realize there's nothing left that's graded except the report presentation. So this week, the lab on next Tuesday is your last lab. So the 2 labs today lab plus homework is your second to last lab. So one part of your painful life is about to change. Now in probability estimation modeling, I'm going to draw the plot a little bit differently than you're accustomed to. So this will be the magnitude of the observation. So think of it as it's still the response. And on this y-axis, is probability. So remember when we did the weights in the classroom, our mean value was, what, 140 pounds or something? So that would correspond to a probability of 0.5. In our case, it was 140. We get here at the, actually I'm doing these backwards. 0.99, very high probability. What would the weight be? It's very likely that everyone in this classroom weighs less than 500 pounds. Or very likely that everyone in this classroom weighs a lot more than 0 pounds. So we might have a value there and a value there. And then if we get to 0.1, the probability of anybody weighing more than 500 pounds in this classroom is pretty small. So here's our 500 pounds. Obviously the scales aren't, I don't want to go to 0 because most stuff is logarithmic. You can't take logs of 0. And we could try to join these together and maybe the probability distribution looks something like that red line. So it's a non-subtle change in looking at a collection of information. The magnitude, the idea that the up-down is still a response is unchanged. But now the predictor variable is no longer some x, it's an estimate of probability of observing that magnitude. So what we need is we need something similar to this green line that works in this space. So what other critters have you seen this semester that work in probability space? Just after the colon. You can say it out loud. There's only 6 people in here. No one's going to laugh at you. Well, they might, but go ahead. Yeah, distributions. So the one distribution we've beaten to death is the normal, but we're going to look at normal as well as abnormal and a few variants. So a distribution in a statistics class was invented to make your lives miserable and confusing, unless you're actually a mathematician or a statistician. All a distribution is some function that in this space will produce some sort of S-like curve. There's a normal distribution. It might look like what I've drawn here. There's other kinds of distributions that have different shapes, and we choose the distribution that either best fits our collection or best fits the underlying process that we think we're trying to explain. Okay, so that was the introduction. That took longer than I needed it to. Hopefully the microphone picked all of that up. Okay, so what we want to accomplish today is creating data models using probability distribution functions. So keep in mind the distribution function is what produces the green line, or in our case, we're using red dots and blue lines, or blue dots and red lines. Whatever one is the line is the distribution function. Forget the thinking concept, because that table is completely wrong. And these get used practically in engineering sense to try to explain risk. So the kinds of extremes that we're interested in engineering, what happens at this end, the common behavior end, and what happens at this end, the rare behavior end. The average stuff is all fine for taxation and so forth, but what's going on at the extreme values is often what matters. Examples of some important extremes are rare events such as floods, nuclear plant explosions, and so forth. Both of those two have happened in your lifetime. You were all alive in 2014. What happened then? Electric Power Corporation, TEPCO, had a plant in Fukushima Prefecture. I think that's the way they name their states. And for some asinine reason, the engineers, yes, ma'am?
Sorry to interrupt. Did you start recording?
God, I hope so. It's showing the little red dealie up here, so a recorder is running. Yeah, you're just planning your weekend sleeping. It's like, I'm gonna need 3 of his lectures to be able to get a good night's sleep in. And that's cool. Yeah, share those on YouTube so that someday I'll get enough subscribers to start monetizing this crap. Which, if the university finds out, they get kind of mad and they fire you unless you give them a cut of the money. Which is, you made $100, we want 110. Okay, anyway, so in 2014, there was a tsunami, or tsunami if you pronounce it the way it's normally said, that clobbered the coast of this prefecture, screwed up the heat transfer pumps in the nuclear power plant, and it melted down, and all sorts of bad things happened. And they didn't even make a movie of it because China Syndrome had been done, and all the pseudo-documentaries of the Russian Chernobyl screw-up have been done. But that happens. Nuclear power plants do fail, and they have pretty substantial consequences. Now, an interesting question outside the context of this class. You know, Japan's known to have tsunamis and earthquakes. How was it that they never occurred to them that, yeah, there could be an earthquake out there and then a tsunami could come and it could clobber the plant? We need to have some backup cooling power there. Nah, that'll never happen. So Japanese engineers are just as screwed up as Americans, are just as screwed up as European ones. Some dumbass lost their trailer because of that. And then floods happen. They're considered rare, but they seem to happen a fair amount of time. Probably because of the society, we don't assign enough rarity to them to be able to. You can't prevent a flood, but to be able to mitigate the damages. And then there's things that happen all the time, almost predictable. In the case of water quality, there's routine discharges from sewage treatment plants. It's pretty much the same every single day. It's going to vary a little bit from day to day, but that's pretty routine. Traffic accidents at a dangerous intersection. I mean, that's almost predictable. When I used to live in Houston, I would drive to work. I worked at University of Houston. I lived on the north side of town. And I'd get on the cell phone and I would call my wife, and it's like, so where are you? Well, I'm at the 610 I-45 accident site, because there was always an accident there every single day. I lived in Houston for 20 years. There's 365 days in a year, so 3,650 twice. So I saw 7,000 accidents at that location. Then there was the 288 45 accident location, which I'd have to pass by. And actually I saw a really good one there once, where there were these 2 people in the car, and they were arguing. You could see they were arguing. All the other commuter traffic were backing off and giving them room. And so there's this gore point where the highway splits. So the highway at that point is maybe 150 feet wide. The gore point is 9 or 10 feet wide. So less than 8% of the open space in front of that car was obstructed, and it center punched that. Bam! Bags, and then the 911 people just got about 100 calls all at once. Yeah, there's an accident at the 288 I-45 interchange. A car just ran into the pavement at about 70 miles an hour. They probably died because that's a little bit too fast to be hitting solid objects. And none of us were going to sacrifice our commute to help
we had to go with 4 lanes of traffic. And so that kind of stuff is fairly common. Another one that you have perhaps experienced in this class is you have something that's due at 11:59. What happens to the network? Yeah, it's game over because it knows. So the probability distribution itself is simply a model of the data. It's simply a green curve. Just like a trend line for deterministic behavior, just like our curvy green line in the trial and error case, just like our interpolating polynomial in the interpolating case. It's simply a function. There's a bunch of them. The ones that you correctly regurgitated on command was normal. Then there's log normal, which is a normal distribution for logs. So in countries where you cut down a lot of wood to make things, you deal with log normals. Now, that was a bad joke. It means the data, the logarithmic transformation of the data is normally distributed. There's gamma, Weibel, which is a special case of gamma. Extreme value, which is the gumball distribution. That's somebody's name. It's not gumballs that come out of a machine. Beta, there's a bunch of them. So we're going to examine a few of these. And we'll see that there's a lot of commonality. They have the added bonus feature that because they were invented by mathematicians for job security on their part, that they use funny letters of the alphabet and they are intentionally confusing to look at. But if you can just remember, they're simply buttons on a calculator. They're just a function. They have alphas and betas that have to be dialed to make them have the shape that you want. That's good enough. So consider our normal density function. The probability density function of the random variable x is this weighting term, which contains a standard deviation, the variable x itself, the mean of the distribution of the population that generates x, and again the variance down here. So in this function, lowercase x is the random variable that we observed. Mu is the population mean, sigma squared is population variance. Now, often we don't actually know the population values, but we take enough samples from the distribution, and if we can assume or convince ourselves that the process is the same every time, we can often approximate fairly accurately the mean and the standard deviation from the sample. And we did that, and we actually saw a really cool thing called bootstrapping, which did it over and over again to approximate the distribution. If we integrate that function from minus infinity to cap x, that result is called a cumulative distribution function, and that's what's drawn over there on the chalkboard on the right, is a cumulative distribution function. The PDF and the cumulative distribution function are conveying the same information. There's no fundamental difference between the two. They obviously look different when you plot them, but they're conveying the same information. However, the cumulative function is in terms of quantiles or probabilities that we are mentally familiar with, whereas the distribution function or the density function is the density of the distribution. Think of it as an object like this paper. It has some density. A density, it's telling you how thick the paper is at any point. We get off here, the paper is very thin because it's non-existent. That density would be 0, and if we integrate from minus infinity, hopefully I'm doing this correctly for you right-handed people out there, towards infinity, we recover all the total probability of the paper. And so there is the quantile function capital F of x, and that's the usual symbology. Here it's shown as a special function ERF, which is called the error function. And the error function is simply that critter, actually this last part of the critter integrated. And not all density functions have closed form integrals like this one. Normal is special. I guess I should have called it the special distribution model. And we've done this before. We can build our own normal distribution models. We do need to use the math package. We need the math package so that we can do exponentials without using the power function and doing semi-infinite series to approximate that. And so we have a density and a distribution. Let me go ahead and load that. And so remember, we also visit our standard normal of mean 0, value 1. Nothing to see there because it's just loading it. And we'll make a plot. And so here is our normal distribution model. The red curve there is the same as the right picture. So the red curve represents a density function or a cumulative distribution. Ooh, good exam question right there. No feedback, huh? 50-50 chance. That's pretty good odds. That's better odds than the Tokyo Electric Power Corporation has for their nuclear power plant. Let's go look at the definition again. Maybe you can figure it out all by yourselves, no help. The red curve looks like it's an integral of the blue thing, so that's one key. And if it's the integral, it's called yay! Oh, where's the scrunchie? I was going to give you your scrunchie. There you go. Oh, it's a little dirty. It needs washing. You at least have enough hair to use one. All right, very good. And the blue curve is the density function. And if we change the value of the mean value of the distribution, let's make it like -3 before I run it, what do you think is going to happen to this picture? I've just changed the mean from 0 to -3. Yeah, I think it's going to move to the left because the way the picture is going to render, it'll look the same, just the axes numbers are going to change. So let's do that. Sure enough, oh, actually, it looks like I forced it to go between -10 and 10. So indeed, it shifted to the left as expected. If we change the value of the standard deviation and make it bigger, what do you expect to happen to the blue curve? It'll get wider, and the red curve will also get wider, but it won't be visibly apparent in the same way. So hopefully that's not too big. Yep, sure enough, you got it right. Okay? Well, you knew you were going to do that anyway. So those are the relationships between the cumulative and the density function. For practical use, the cumulative function is what we're going to use. And we're going to try to put our values of the random variable and get them to fall on this red line, or actually more importantly, try to get the red line to pass through the values of our variable. And that brings us to the next thing, which is a concept called exceedance probability. So the purpose of a distribution model is to explain data and allow us to make an estimate to answer the question, quote, what is the probability we will observe a value of the random variable less than or equal to some sentinel value? So a common way to plot the quantile function is with the accumulated probability on the horizontal axis and the random variable value on the vertical axis. And so here is an example of a frequency plot. In this example, the blue curve represents our data model. If it was just dots, it would represent data. And we've selected a random variable value, looks like about 10, 100, 90, 80, 70, around 50,000 is this magenta line. So if we take the magenta line, move horizontally from 50,000 until we hit the data model, and then read downward, we come to a probability of 0.1. So to the left of that is called the non-exceedance probability. And the way to interpret that is it says that the probability of observing that magenta value of 50,000 of that value or less is 0.1 minus is 1 minus 0.1, so it's 90%. So non-exceedance probability is 90th percentile. The probability of seeing 50,000 or more is the 10th percentile. And sometimes the plots are presented in reverse order, so you, the human, has to take a look at the plot in order to infer whether it's an exceedance or a non-exceedance plot. It's usually not necessarily pretty obvious in plotting, but it's usually obvious when you make your estimates. And if the estimate seems to be the wrong probability, just take that value, subtract it from 1, and that's probably what you're after. So in the figure shown, we would write that the probability of observing x less than 50,000 is 1 minus 0.1 or 90% non-exceedance. The probability of x bigger than 50,000 is 0.1 or 10% exceedance. And then you can read the words there yourselves faster than I can read them to you. Another way to look at it is to simply recognize that the blue curve in that is the quantile function f of cap x, with x plotted on the vertical axis and the quantile plotted on the horizontal axis. Now let's put these ideas to use. We'll sample from the population of integers from 0 to 100. You remember those things. And we'll, as we take them out of the bucket, we'll write them down and then put them back. And we'll use a uniform distribution where a single pull from the population is likely. And then we'll do 25 of them, roughly a quarter of the total number collection. But we don't know the size of the population. And because we're doing replacement, it kind of doesn't make sense. So we're going to take 25 numbers out of a bucket. That bucket contains 101 balls. Each ball has a number on it, 0, 1, 2, to 100. And as we take it out, we'll write the number down and put it back in. It's what the Lottery Commission wishes they could do, because they would be able to keep even more money. So we're using our friend NumPy, and we're using the random choice function, which you've done before in different parts of the class. So the sample's been collected. Let's get some statistics. Let's sort the sample in place, and now we're going to do something interesting. We're going to create a function called Weibull plotting position. If I took one ball out of the bucket and that one ball represents 1/101th of the total content of the bucket, we could assign the probability of that ball 1 in 100. If I take two balls, I should get two different numbers because I haven't replaced them. The second one has a 1 in 99 probability. So that way of expressing things is a way of using a plot where on this axis we're going to have Weibull plotting position, and there are other plotting position formulas, and it's simply based on the order of the number. And so we rank the results, we rank those 25 balls that we get out, and we say that any number that we got was equally likely from whatever the underlying population is. We sample 25 times, so the first one has a 1 in 25 chance, the second one has 2 in 25, 3 in 25, and so forth. And that will let us represent our balls like that. And I took advantage of the curve being up there, so that's a really good fit. This is the key thing, that the plotting position is simply a formula. If we go down to the bottom, I'll show you what the formulas look like. So there's some of the formulas. So the California method, somebody was having fun with table making. That is not how you spell California. They would have to tax you for that extra L. Is you take the rank and you divide by the total number of things. There's a Hazen, Weibel, Beard, Bernard, I can't pronounce that one, Bloom, Tukey, Gringorton, which is a fun one because it sounds like some kind of creature out of Guardians of the Galaxy, Cunane, Adamowski. There's got to be dozens of other ones. And they all tend to have this structure where the empirical exceedance probability, cap P, is equal to rank minus some constant B divided by how many things that you sampled plus 1 minus twice the constant B. So that's a plotting position formula. And we'll see its purpose in a second. Let me get back to wherever I was. I think I was right there. There was a reason I highlighted that. Okay, so we've now generated the plotting position formula, and let's plot what we have. Okay, so we haven't put any effort into trying to fit the normal distribution. We have these blue dots, which represents our sample from our bucket that contain the numbers 0 to 100, and they've now been ordered from small to big, and then each one in the order has been assigned a plotting position, and we can't see much from that, although we can actually get a pretty good estimate of the median. The median is the 50th percentile, or the 0.5 quantile. So if we go up from 0.5 to where our eyeballs say our blue dot function is, and then read left, we're about 42. Let's see if we have median available to us. If we do, what would it be? Median? It would be sample. I don't know if the method's actually available, so we'll just. Oh crap! I hate it when that is. Let's do the mean value, which I'm pretty sure is available. That should be close. So we'll come up with 43 or something. 43.12. So that's amazing. It's almost as if I've done this once before. So that's from our empirical distribution. We can estimate means, and we could probably come up with a standard deviation. We're not going to do that. Since our goal is to make our red curve go through our blue dots, we probably need to jack with our red curve a little bit. Let's see where the red curve came from. YCDF. So our red curve is still way back here. Yeah. Well, now that we've gone to the trouble to estimate the median, 43, we're going to go ahead and put that in. I have no idea what the standard deviation is. But now we should have updated our curve. Let's see what happens now. Even worse. I may be leaving a step out. Don't care about that plot. Oh, now we're resampling everything again. That was stupid. Anyway, our current plot is terrible. Now let's use some sample statistics to fit the data model. So back here, we just used a formula that would fit our data to produce our interpolating polynomial. Here we use trial and error by just guessing values of alpha and beta. Here we used essentially linear algebra to minimize the sum of squared errors. Here we're going to take the sample mean and the sample standard deviation and use that to adjust the value of the green line, or in this case red. So we will declare the sample mean is equal to mu, and the sigma is the sample variance. And let's see where we calculated those, because we can't do that. Okay, we calculated it up here. So now let's go ahead and we've regenerated the model. And now when we do the plot, our red curve goes nicer through the blue dots. All of that kind of looks nice. So it says our sample variance is 1,000. Let's go back and fix this one. No, it's still not working quite right. This one works right, so don't try to do what I did. Okay, so we could, these numbers are between 0 and 100, and they're integers. They are not likely to be normally distributed. If we took enough samples, we would expect the blue line to just be a diagonal line from this corner to that corner. But with a subset of it, our normal distribution model is usable. I would say this one's usable. It's not by any stretch of the imagination perfect. I wouldn't bet my life on it, but yours, I wouldn't have a problem with that. So we have the advantage of knowing everything about the population. We know the population are the numbers 0 to 100 integers. So we can calculate the population mean, which should be either 49 or 50. I can't do it in my head. And we know the population standard deviation. So we can calculate those directly. And so let's now put the population values into the model instead of the sample values. And when we plot that, it's going to look kind of similar. So we created an example where the sample was big enough that it was a good representation of the population. Now, some observations. Our actual population is a uniformly distributed collection. By random sampling and keeping the sample size somewhat small, the sample distribution appears approximately normal. Things that we do in engineering are not always bounded, and most of the time they're not. And the choice of the Weibull plotting position is not entirely arbitrary. I didn't pick that because it was the easiest, because the California method is the easiest. I picked it because I wanted to my distributions, and the Weibull plotting position is good at that. Now let's apply this to something real. So we're going to look at a file called Beargrass Creek. If you want to do this yourself, you can download the file from that URL. And we're going to, we'll actually go look at the contents of the file real quickly. Scheiße. Where'd everything go? So here's what the file we look at. It has years in one column and peak discharge in another column. It could be any other variable where we're going to just study the peak column. It doesn't have to be flows. It could be, I don't know, breaking strengths of some material that takes care of mechanicals. What other engineers we got in here? The voltage before something converts from a physical object into smoke, because everyone knows electricity is just compressed smoke. Proof. Anything you've ever experienced in your life that was electrically powered that failed, what came out of it? Smoke. So electricity has to be compressed smoke. Chemical engineers, I got nothing for you. Any chemicals in here? Good. Yeah, make friends with them because they're going to be rich or dead. So we're going to read that file and we'll analyze it. We're going to use pandas because that's a convenient way to read files. And you notice in my example here, I'm reading directly from the directory, so hopefully it's already there. For you guys to do it, you actually have to download the file to your computer, or you already know the 4 lines of codes to automate that. Commit it to memory, right? As if. Okay. Did not find the file. Let's find out what's going on. Didn't want that to happen. That's weird. Let's see if I remember how to do this. CD. I don't normally do shell commands from, oh, it's ignoring me. Oh, it's very much ignoring me. All right, let's see if we can't get this. Boy, I hope it doesn't clobber what was already there. I bet it did. Okay, let's see, this is Jupiter. I do not know why it's not functioning right now. We're going to go with it's a piece of crap. Okay, so that get me in, and how do we change? CHDIR. I guess I should actually look at the syntax. We'll find out in a second. Yeah, that's not the right one. Probably has to be in quotes. Yeah, dumbass. You knew that. Hopefully this doesn't happen to you all too often. Okay. Then, so we've gone back up to lessons and we want to go to Seriously. Okay. Yay. I don't know why I had to do all that. It was just, I have a feeling that thing where it's trying to load in, having me update something is the problem. This only has to work for about 3 more weeks, and then I can repair it. So we have imported the file. If anyone was paying attention what I did, I was just doing shell commands directly in the notebook. And now we can make a plot of the file. Wonder if this will actually work. Oh, it does. So there's a plot of the data. The blue line is of absolutely no use. It's representing the year. The horizontal axis is just the index of the object. So 0 through 31, there's 32 things. The orange line represents the peak value. So if you can mentally ignore the blue line, what can you say about the peak value? So these are representing peak stream flows in Beargrass Creek. In the early part, they're less than 2,000. You have 1, 2, 3 that are bigger than 3,000, and they occur kind of in the second half of the time series. What's the average peak value? So I was about to call your name, Mateo. You're about to fall asleep again. I know I'm boring, but you can't really tell. Somewhere in the 3,000 range, maybe, or 2,500. Let's just apply the miracle of cut and paste and see what these look like in our normal distribution model. So all I did was cut and paste the Weibull plotting position function and the normal generating curve. Oh, you can see much more on my computer than you can up there. There we go. And is the red curve an okay approximation to the blue dots? I'd say it's okay. It's certainly better than what we had before. So if I was to ask you, what's the probability of observing a discharge bigger than 2,600 discharge units, whatever the random variable value is? How would you answer that question? I don't know is not an acceptable answer. Try again. So I said probability bigger than, what did I say, 2,600? So you find 2,600 here. It's right about there. You move horizontally until you hit what? The blue line or the red line?
Red.
The red line. Then we read down, and we're pretty close to 0.9. So the probability bigger than is going to be that remaining 10%. The probability of seeing 2,600 smaller than is going to be the full 90% because of the way the quantile value is plotted. We don't use the blue dots after we have fit whatever our distribution model is. And the reason we do that at all is, what if I want to assess the probability of seeing 6,000 or greater? I don't even have that in the blue dot world, so I can't. I mean, I have to pull it out of my datum. But I do have a red curve here, so I can perform the miracle of extrapolation and make that statement. So that's what the people at the Fukushima power plant should have done to figure out the probability of an earthquake and a tsunami clobbering their power plant and making everybody in the prefecture glow in the dark. Which is handy because they didn't need streetlights anymore. So let's go ahead and describe our data. So we have a mean value of 1,600, standard deviation of 1,000. The biggest observed in the data is 5,200, so we can't even answer questions about 6,000 or bigger. But let's suppose we wanted to know what the associated estimated probability is of a value of 6,000 or bigger. We can assign 6,000 to a variable named myGuess because I have no better name for it. We can print the mu and sigma that we've already calculated, and we can put that into our normal distribution. Run that, and it says 6,000 represents the 99th percentile in our quantile function, which means the chances of seeing 6,000 or greater looks like less than 1%, very unlikely. The chances of seeing 6,000 or less is almost 1, so pretty darn sure. And if we want to get fancy, we could use Newton's method, which is not only does it make a great cookie, fig-filled, it can systematize this part, because as of now, all we have for predictions is trial and error by using myGuess. And so we use Skippy optimize, we build our function, and we're looking for quantile 99.99, let her rip, and turns out the 5,820 units represents the 99.9th percentile, or 0.01 percentile of being bigger than that. So a peak discharge of 4,000 or so is expected about 1% of the time, and the key thing here is notice that we took the value from the fitted distribution. So once we've taken the observations and passed a distribution model through them, our green curve over there on the right, we make all of our estimates on the model. So how are we for time? We got enough time? 10 minutes? Yeah, we can do this in 10 minutes. Another data model we can try is called log normal. And so we take a normal distribution and we beat it with a log. Walnut is the best log, but oak is a little bit more common. You want to use a hardwood because you don't want the log to break as you're beating the data. There's nothing more annoying than beating data and having the log break, and you have to go get another log. So all we're going to do is logarithmically transform everything by applying a function called logit. Hopefully that was already, there it is, defined up here. Remember how to apply functions. You've done this already. Most of you did it on exam 2. Amazingly correctly, and there were other problems that people couldn't get correctly. It's just baffling. And here we have a sample mean and a sample variance of the logarithmically transformated stuff. And then we will sort it, we'll build the plotting position, and then we will fit the model in log space and then plot it. So we do that, and there is our logarithmic transformed, and visually that looks even better because it looks like everything's closer, but that's a trick of the logarithmic transform. Let's put it back into original arithmetic space, and so now we're going to have an anti-log function. She hangs out with Uncle Log, but anti-log, and we will apply that to recover what it looks like in regular space. And there is our log transform data model. And then you have to make the decision. Do you like that better than the normal distribution? It certainly fits, with the exception of the last 3 dots, it certainly fits the data better. So that perhaps might be a better choice. And these might be outliers or out-and-out outliers if they're selected. And now we can go ahead and make guesses of probabilities associated with particular values. So for example, in the log normal model, a observed value of 4,440 has a quantile of 0.99, or there is a 1% chance bigger than 4440, 99% chance less than. If we want to get fancy, we can optimize. And now that we have a decent method, one would want to put stuff into functions to keep the code concise, and that's what the mighty internet does, and you get packages. There are some other useful models available. One is the Gumbel distribution, also called the double exponential. There's what it looks like in arithmetic. This one has the added bonus feature that the alpha and beta, because they appear as ratios everywhere, there is no realistically convenient way to find them by any variation of this. But it turns out if you can do nonlinear algebra and all that good shit, you can come up with an approximation for alpha is equal to the mean times the square root of 6 divided by pi. I shudder to think of how many hours were spent pulling transcendental functions out of their datum until they came up with that. And beta is 0.45 times alpha, where mu and sigma squared are the sample mean and variance. So we'll go ahead and perform the same analysis using this function. And there is our double exponential fit. I would say not quite as good as log normal anymore. But if we want to look at the 1% chance, we can apply the same approaches. And there we go. And the last model I want to consider is one that's specifically stipulated for use by federal agencies for probability estimation of extreme hydrologic events. The data model is called log Pearson type 3, but it's actually a gamma distribution. And so in this example, we're going to dispense with building it in Python primitives, and we're just going to use a package. The density function is not hard, but the quantile function is elaborate. So we're going to let Google do some work for us, and if we search the term gamma quantile function Skippy, we get this nice blog entry, which is a good start. Here's what the Pearson type 3 density function looks like. Is this thing here with the cursors. And look what we got. We got betas, we got taus, we got alphas. That's pretty cool. That's like 3 Greek letters. That'd be the name of our collective fraternity or sorority, the tau alpha beta. Is there one? Oh, there needs to be one. That would be a cool one. But it will also have this gamma function, which is a function, not a parameter. So gamma, tau, alpha, beta. I wonder if you can spell anything. You can spell bat with that. If you do beta, alpha, tau, their symbol would be a bat. That would be cool. So we'll make some substitutions and we can kind of reduce the letters of the alphabet a little bit, where we have alpha, lowercase gamma, and that's it. And with those, we get our density function, and that's now called a one-parameter gamma density function, which is just like the example. And then we can read from another document and figure out how to get the values of the alpha. Now we have almost everything. We've got the name of the function in Skippy. We want to get the CDF function, so let's go to tool to generate all Pearson type 3 and class paragraph 2. And here I have a statement that uses a lot of glue. So by now, you've been in the class 3 months. You are the crazy ones that come every time. Mostly what we've been doing is teaching how to glue stuff together. Pull parts out of that, you glue them together. And again, hopefully you get 24 points. Although it's been graded in a long time. And that actually is the point of the class. I know there's some at the team meetings, there's some concern that we're not teaching the programming, but as a practical matter, you'll be much better served knowing how to glue. Some sometimes you have to do both. Okay, so let's get the glue out, and we'll use our logit function that we've already invented. Anti-logit, Weibull, already built. We just put those in as functions. And then we'll get the gamma CDF function, and we're going to pull it from Skippy stat, and then we're going to feed it its parts in the fashion that it's expecting so that we can get the distribution function back. And then finally, we will just plug everything into an estimator, make our plotting positions, build our model, reverse transform everything, and plot it. So let me go through those steps. I hope I didn't miss a block. So that one worked. Gamma's built. Samples are built. We'll build a plotting position. We built the red curve. And now let's look at everything graphically. And so there's our log Pearson type 3. Now the log Pearson type 3 is designed to work better at the right side. So it's not unusual that it looks kind of goofy at the left. And then that vertical drop, I think, is a consequence of my programming. And just as before, we now can answer questions about the underlying process. We can get fancy with Newton's method. And if we're looking at the 99 percentile non-exceedance, so 99% of the time it'll be less than, 1% greater than, we come up with a value of 5,856. So 5,856 data units corresponds to the 1 percentile bigger than, 99 percentile smaller than. So as President Reagan once said, trust but verify. Let's make sure that that kind of makes sense. And if we take the gamma distribution with all the information input, we get 90.9753, which is not 0.99. That's almost a little bit too much difference for comfort. But we'll just continue because apparently the class that starts at 9:30 wants to get in here at 9:10. So let's summarize what we've gone so far. If we use a normal model, our 99% peak flow is 3902. Log normal 4433. Gumbel 3296. Log Pearson type 3 5856. You could argue that log Pearson type 3 is the best of the visual fit. It's also the highest number, which makes sense for a federally mandated thing. They want to guarantee that the lawsuits are rare so that the elected people have time to get into their private jets and move to a country that doesn't have an extradition treaty with the United States. So at this point, we have to choose our model, and then we can investigate different questions. So let's suppose we decide log Pearson type 3 is our favorite, although we don't have to decide that because it's been decided for us because it's a mandated distribution for this particular type of data. If we want the 25% exceedance probability, that would correspond to a value of 968 flow units. 50, the median is 1302. The 75th percentile is 1860. None of those three are particularly useful in a practical sense. A 90th percentile, 10% chance or greater. 99th percentile, in flood statistics, that's the 1 in 100 year event. And if we were designing some engineered object, generally it's required that it's designed to survive whatever the magnitude of that event is. It doesn't have to be serviceable during the event. It has to be there after the event's over. So the Tokyo Electric Power Company, they blew it on that. Their thing was gone, although they have really good lighting that just follows people around everywhere. We could go even higher. So the 1 in 500 year chance event, there's no common stipulation of that in the U.S. And then the 1,000 year event, I think, is what is used in the nuclear power industry in the U.S. So it has to survive that. So in the case of this Beargrass Creek, it would have to survive 11,455 flow units, whereas the biggest one we saw was 5,000 in the data. That's very unlikely to happen, but we have departed the world of whether something is physically possible to whether something is we can. What the hell just happened? Well, fortunately, it was near the end of the lesson. Oh, now it's not typesetting. There we go. Those look different now. We could use Newton's method to fit all these things. And then the last part, you can read this on your own, is just a little bit of discussion of some different plotting positions. And in 15 minutes, we will have lab number 21, which will be pretty much doing what I just did here. Hopefully, Josh has had a chance to look it over and get it to work for himself. So thanks very much for your attention. And let's see, you were Jasmine. That's who you are. So you coming to lab today, Jasmine? Or are you going to blow us off again?
I will go to lab.